Let's study 9th Standard ICSE Physics, Chapter 5, Section A, Upthrust and Archimedes' Principle. Now, let's start with the topic of upthrust, also called buoyant force. Whenever you enter a swimming pool, you feel lighter. An object might require some force to be lifted in air, but that same object in water can be lifted very easily. It's almost as if there is a loss in weight in water. In fact, this happens in any fluid, any liquid. This is because of an upward force in that fluid, and that is called the buoyant force or upthrust. That is the reason why things float. For example, Titanic was such a huge ship, so heavy, and yet it could float on the ocean water for a long time. How could it? Yes, you may answer that its overall density was less than the density of the ocean water. But yet, what is it that keeps it on top of the ocean water? It is the buoyant force. So, let's take a few examples here. There's a beaker filled with a liquid, let's say water, but all liquids exert upthrust, by the way. And there's an object. Let's say its weight is 15 kgf. I could have used 15 Newton as well, which is the SI unit of weight. After all, weight is nothing but force, a gravitational force acting downwards. So this weight is acting downwards, and I can measure it with the help of a spring balance. But I need not show this every time now. It's understood that I'm weighing it with an instrument. When I immerse this in water, like this, and now if I measure its weight with the same spring balance, I will notice that it has decreased. Perhaps it's just 12 kgf now. It's become lighter. But this loss in weight is apparent. It's not real. If I remove it out of water and again if I weigh it, it's going to be 15 kgf. So if you want to lose weight, going into the swimming pool is not a permanent solution. The loss in weight is apparent. It's an apparent loss in weight. That means it appears to lose weight. It's not real. But again, what is the reason behind this loss in weight? And understand that there is no loss in mass here. There's a loss in weight, which is the gravitational force acting on it. You see, even here, 15 kgf of gravitational force is still acting downward, but there is yet another force being acted on it, and that is the buoyant force or the upthrust, which is 3 kgf. So the net result is 15 minus 3, 12 kgf downwards. So the loss in weight is 3 kgf, which is nothing but the upthrust, and the apparent weight is 12 kgf, even though the real weight was 15 kgf. It's like if you're lifting a heavy load, it's taking you 15 kgf to lift it, but a friend gives you a helping hand and applies some force from the bottom to help you out, and he's applying 3 kgf of force himself. Then now you will not have to apply full 15 kgf to lift it. You will now have to apply less force, only 12 kgf to lift it, thanks to the helping hand. Upthrust is that helping hand, which decreases the weight. But why is there an upthrust exerted by fluids? Well, we can understand this with the help of what we studied in the previous chapter about the fact that as the depth in a fluid increases, the pressure, liquid pressure also changes. So in a liquid, let's say there's an object here, liquid pressure is being exerted on it from all directions. Now we know that at the same height or same depth, the liquid pressure is the same. So they will cancel each other out. However, if you talk about the overall pressure on the top surface and the overall pressure on the bottom surface, there is a difference in the pressure, because this pressure P1 is at a lower depth and this pressure P2 is at a greater depth. So which pressure will be greater? Definitely the pressure here will be greater than the pressure here because of the difference in the depth. P1 is at this depth and P2 is at this depth. Greater the depth, more the liquid pressure. So the upward pressure is greater than the downward pressure. This difference in pressure is the cause behind the upthrust. This difference in pressure, that is P2 minus P1, multiplied by the area of contact, gives us the force. Force is pressure into area, and here the overall pressure is acting upwards, so the overall force is being exerted upwards. This is the origin of the buoyant force. Now let's take another example. Again, I have an object, but this time let's say it's just weighing 3 kgf. And when I immerse it in the liquid, let's say water, what if, once again, the upthrust is 3 kgf? So the weight, that is the gravitational force of 3 kgf is acting downwards. The upthrust of 3 kgf is also acting upwards. So what will be the net force acting on it now? Well, it will be 0 kgf. That means it will become weightless, which means it will float. But it will float just under the surface of water. It will be completely immersed. No part of it will be above water, but it will float because no force is acting on it, net. So whenever the upthrust is less than the actual weight of the object, it will sink. However, it will sink slowly. If I release this 15 kgf of object in air, it will fall to the ground very quickly. So it will take just 2 seconds. But this same object, when dropped in a swimming pool, it will reach the bottom quite slowly. It won't travel as fast as in air because now it is not being pulled down by 15 kgf force net. The net force acting on it downwards is just 12 kgf. So its acceleration seems to have decreased in water or in any fluid. Is there any upthrust acting here now in air? Yes, there is. I told you upthrust is exerted in all fluids, even gases. But gases' density is so less that the upthrust is negligible. Let's say it's 0.001 kgf. Now, we can't detect such a change in upthrust with the help of the normal spring balance. So, we don't detect any loss in weight in air. But there is an upthrust acting here. In fact, if this object was weighed in a vacuum, complete vacuum, perhaps there a very sensitive spring balance will give you a slightly higher weight. Let's say 15.001 kgf. So why is the object weighing more in vacuum compared to in air? Because in air there is an upthrust on this marker. There is an upthrust, but it's negligible because air is very rare. The density is very less compared to water. Well, the upthrust is a lot. So in water, we can see some significant difference in the weight. In fact, if I replace this with mercury, which is a very dense liquid, 13.6 times denser than water, then the upthrust will also increase. You see, upthrust depends on a few factors, and one of those factors is density. The denser the liquid, more is the upthrust, and easier it is for us to float in it, or for any object to float in it. So if this same 15 kgf object is now immersed in mercury, it's possible that the upthrust will also be 15 kgf, in which case it will now float. That's what happens with iron. If you have an iron object, an iron ball, and you put it in water, it will sink, obviously, because not only is iron's density more than the density of water, but you should also say that the upthrust exerted by water is less than the weight of the iron ball. So from now onwards, and give reasons, you have to say the answer not only in terms of density, but also in terms of upthrust, which is the actual reason. But if you keep this same iron ball on mercury, it will float. That's because, yeah, iron's density is less than the density of mercury, but also because the upthrust exerted by mercury will be greater than the weight of the ball. So let me just solve that now. What happens when you put it in mercury? You know that it will float, but let's understand it with the help of some values. Beaker filled with mercury. So we've got iron ball, 15 kgf is its weight acting downwards. We'll dip it in mercury now. If it was completely dipped in mercury, then the upthrust acting on it, let's say, is 20 kgf. Well, that's more than the weight of the object. Earlier, we considered two cases in which if the upthrust is equal to the weight, like 15 and 15, then the object will float exactly under the surface of the liquid. And then we saw the case where the upthrust is less than the weight of the object. In that case, the object sinks. So those are the two cases. Weight greater than upthrust, weight equal to upthrust. Understand that when weight is equal to upthrust, the net weight is 0. It's apparently weightless. It's floating, but it's completely submerged. Now, this is the third case where weight is less than the upthrust when completely submerged. I'm stressing on this sentence, when completely submerged. So what will happen now? Will it sink? Obviously not. Will it float? Yes, but there is a net force acting on it. It is not weightless per se. It's actually 5 kgf of force acting upwards. So will it start flying like a hydrogen or helium balloon does? If I have a helium balloon right now in air, it starts rising up, right? It floats and it rises up. Why does it rise up? Yeah, because it's lighter than air. But why? Well, that's because air exerts an upthrust, a buoyant force. Now, on things like markers and on us, it's negligible because our density is a lot and air's density is nothing comparatively. But hydrogen or helium balloon, that is so less dense that its weight is less than the upthrust acting on it. So, in case of a helium balloon, the upthrust is greater than the weight. So, what is the net force? The net force is acting upwards, and that is why the helium balloon rises up, because of upthrust. But here, it's a liquid, not a gas. So, what's going to happen is, when we immerse it with our hand, we will notice that there is an upward force acting on it. Understand that this iron ball is immersed in mercury here, not water. So, it wants to float. If I release our hand, it will bob up. And look how it will seem to be. Like this. So, it will be partially submerged only. And now, I would say that the upthrust is 15 kgf. And the weight was, of course, 15 kgf. So now it's weightless. Once again, the net force is 0. 15 minus 15 is 0, and it will float. But it is floating partially, with part of its body submerged and part of it above the surface of water. So in both these cases, flotation happens. And in both the cases, finally, the net force becomes 0. Even if the upthrust was greater than the weight, in liquids, ultimately it will adjust itself so that the upthrust becomes equal to weight. But how does the upthrust decrease? It was 20 kgf. How did the upthrust become 15 kgf? Well, notice that here the object was completely submerged. Now, if I had an opening out here and a eureka can, eureka means I found it. There's a story behind it, wherein Archimedes yells eureka, eureka when he discovers something. More about it later. So when I immerse this object in this liquid mercury, some of the mercury will be displaced by it, and let's collect it in this beaker. Interestingly, if you weigh this mercury, it will turn out to be 20 kgf. This is fascinating. Weight of liquid displaced is equal to upthrust. Remember, this is a key concept in this chapter. Yes, the volume of the liquid displaced is equal to the volume of the object submerged in it. Obviously, the volume is the same. But another thing which we have to remember is that the weight of this liquid will be equal to the upthrust being exerted on the object. Now, did we need 20 kgf of upthrust to make it float? No. All we needed was 15 kgf of upthrust, which was enough to cancel out this weight. So now when we release our hand, it will no longer sink entirely in mercury. It will come up a bit. You have done this with a plastic ball. If you put the plastic ball in water, it will be submerged entirely. But when you release your hand, it comes up to the surface with part of it submerged and part of it not submerged. But why like this? And how does it decide till what level should it be submerged and what part of it should be above? Well, look here. Here now it is submerging only this much. So imagine we started a fresh experiment, and this time I didn't force the iron ball inside. I gently kept it touching the surface of mercury and I released it. Slowly the iron ball will dip inside and it will start floating. The iron ball is floating in mercury. This time also some mercury will be displaced. Let's see how much. We will again collect it in this Eureka can or this beaker. This can with this mouth, that is called the Eureka can actually, not the beaker. So this is the Eureka can with this mouth or spout. This is just an ordinary beaker. Now if you notice here, the mercury displaced is a bit less compared to the mercury displaced here. That's because here the entire object was submerged. Let's say its total volume is 20 centimeter cube. So the volume of mercury displaced is also 20 centimeter cube. And here the volume of this iron ball submerged is, let's say, 15 centimeter cube only. So only that much mercury will be displaced. So it will be 15 centimeter cube of mercury displaced. And since this is less mercury, its weight will also be less. And guess what will be the weight of the mercury displaced here? Yes, it is 15 kgf. So that's why the upthrust has decreased now. Earlier it was 20 kgf, now it's just 15 kgf. That's because less mercury is displaced, and that's because less of the iron ball has been submerged. So the part of the iron ball submerged will be just enough to create upthrust equal to its own weight. That's a very significant sentence here if you think about it. So in the Atlantic Ocean, if the Titanic is floating, it will submerge just enough so that the entire water displaced by it is equal to the weight of that seawater displaced by it is equal to the weight of the entire ship. Let's say the entire ship has a weight of, I don't know, X kg, what, 100 tons, 1000 tons, X kg. Of the entire ship, not just the submerged part of the ship. I'm saying the entire ship's weight is X kg. So in order to float, it should have an upthrust of X kg. Only then it can float. In fact, I should say X kg F, because it's weight and kg is a unit of mass. In order to generate an upthrust of X kg F, it will have to displace the water whose weight is X kg F. So the weight of the water displaced, this much water, which is a lot of water because Titanic is a huge ship, and if you notice a huge part of it is actually submerged in the ocean water, and if we had a beaker big enough to collect that displaced water and weight, it would be so many tons of kgf or x kgf. So that's the law of flotation. More about it in a different section here. But now we understand the reason why this concept of buoyancy is important to understand why things float and how they float, how much is it submerged. Now there is a formula, weight of liquid displaced is equal to upthrust, which is also equal to the apparent loss in weight. That means the weight decreases by a quantity equal to the upthrust acting on it. Let's take more examples to understand this. So initially we had the weight as, let's say, 15 kgf. We submerge it completely. The weight of the liquid displaced is, let's say, 12 kgf now. So the upthrust acting on it is 12 kgf. So if the upthrust is 12 kgf, question number 1, will float or sink? It will sink. What is the apparent weight now? The apparent weight, also called the net force, the apparent weight is 15 minus 12, 3 kgf. That means we've got 15 kgf acting downwards, 12 kgf acting upwards, so the net weight acting on it is 3 kgf downwards. Also remember that the weight of anything acts at its center of gravity, which is here, downwards. Whereas the buoyant force acts at the center of buoyancy, which in this case is the same point, the central point. This would be a better diagram. This is the weight acting downwards, this is the buoyancy acting upwards. Anyway, so the apparent weight is 3 kgf. It's become so light in water or in the liquid. There is a loss in weight. What is the apparent loss in weight here? 12 kgf. It has lost 12 kgf of its weight. Due to dieting? No, because of upthrust. So the apparent loss in weight is equal to the upthrust, which in turn is equal to the weight of liquid displaced. This is the master formula for this section. You need to remember this. And for numericals, the formula we have to remember is that buoyant force or upthrust is equal to V rho G. V means volume of the liquid displaced, of course. It depends on volume. More the volume of liquid displaced, more is the upthrust generated. Volume of the liquid displaced is equal to the volume of the object, part of object submerged. It is not equal to the volume of the entire object. For example, in this case now, the object is floating. So the volume of the liquid displaced is equal to the volume of the submerged part of the object. So remember that. So upthrust is equal to volume of liquid displaced. I can write an L out here. Next, rho, that is the density. Again, density of what? Density of the liquid. We know this. More the density of the liquid, more is the upthrust. Mercury's density is more than that of water. That is why mercury can exert more upthrust. And that is why iron nail, which sinks in water, can float on mercury. By that logic, tell me, if you were in a lake, freshwater lake, and you were in the ocean, which is very still, in which case will it be easier for you to float? Well, if you see, the ocean water is very salty. So its density is more, much more than the freshwater lake water. If the density is more, then that means upthrust is more. So if this ocean is exerting a greater upthrust, isn't it easier for us to float in it compared to the lake water which has fresh water? That's why it's easier to swim in seas rather than in rivers, because seas are salty and more dense and more upthrust, so that you will sink less in seas compared to in river water. In fact, the Dead Sea is so salty, the saltiest sea in the world. The upthrust provided by it is so great that anybody can float in it, even if you don't know how to swim. You can literally just float and read a book out there. But make sure no water gets into your mouth. It's Dead Sea, and the name means it's deadly. It's very toxic, such high concentration of salt. So here, perhaps the weight was 15 kgf, and the upthrust is how much? Can you guess? 15 kgf. Obviously, whenever anything floats, be it completely submerged or partially submerged, if it is floating, that means upthrust is equal to the weight. Only then it will float. What is the net weight here? 0. What is the apparent loss in weight here? 15 kgf. It has lost all its 15 kgf. That is why it's floating. So when we do numericals, you'll get used to handling these numbers and calculating these values. But right now, understand the concept clearly. Now, coming back to this diagram wherein the object was floating with a part of it only submerged, let's identify where is the center of gravity and the center of buoyancy now. Ideally, they are coinciding, but when the object is completely submerged. But now, what is it? The center of gravity is obviously here, the midpoint or the center point of the sphere. But the center of buoyancy would be the midpoint of only the submerged part of it. So let's say it's approximately out here, the midpoint of this. So in such situations, the center of buoyancy, that's where the buoyant force is acting, and the center of gravity, that's where the weight is acting, do not coincide. So that's all you need to know. So I hope you've understood it clearly, this concept. So are you ready for a challenging question to test your knowledge? Alright, tell me, I have this object here. Let's say this is mercury and this is an iron ball, and the iron ball is of a particular radius. It's floating obviously because its density is less than that of mercury. In another beaker, I have, let's say, aluminium ball. Even the aluminium ball is floating, but you can see that it is submerged less compared to the iron ball. It is also floating in mercury because its density is less than that of mercury. So first question is, whose density is greater, iron or aluminium? Well, it's aluminium. Aluminium is lighter than iron. That is why it is submerged quite less and iron is submerged quite more. Now in this sum, I'm keeping the radius same. Okay, if the radius is same means the volume of the aluminium ball and the iron ball is same, the total volume, because the radius is same. Next question. In which case is a greater upthrust being applied? In which case is a greater upthrust being applied? Well, definitely it is iron. You see, iron is displacing so much of mercury, so definitely the upthrust would be quite high. Let's say it's 12 kgf, which would be sufficient to be equal to its weight and make it float. And here it's displacing less mercury, so the upthrust will be less, let's say 7 kgf. Again, that is enough to make it float. So now we see why aluminium sinks less, because it needs to displace less mercury to float, because its weight is only 7 kgf. It needs only 7 kgf of upthrust. Whereas iron, whose weight is, let's say, 12 kgf, being denser, needs 12 kgf of upthrust to float. So it will displace mercury, whose weight is 12 kgf. Okay, now next question. Let's take water. Let's put this aluminium ball in water. This completely submerged. And now let's take the iron ball. Even that is completely submerged in water. You know, both of them will sink in water. Radius is same, by the way. Aluminium is lighter than iron, but both of them will sink in water. In which case is a greater upthrust being exerted? Tell me the answer. I mean, think about the answer. Well, a greater upthrust is exerted. Well, the upthrust exerted on both is same. It is exactly same. See, the volume of the aluminium ball and the iron ball is the same. That means they are displacing the same volume of water. That means the weight of the water displaced by both of them is same. That means the upthrust exerted on both of them is same. Let's say the upthrust on this is 2 kgf and the upthrust on this is also 2 kgf, because the water displaced by them are also 2 kgf respectively. Yes, in both the cases, the 2 kgf was not enough to make them float. What was the aluminium's actual weight? As I said, it was 7 kgf. But its upthrust is only 2 kgf. Is that enough for it to float? No. What is the net weight with which it will fall down? 5 kgf. Because there is a loss of 2 kgf. Similarly, the iron ball's actual weight was 12 kgf in air. So is 2 kgf of upthrust enough to make it float? No, it will sink. And what is the net weight with which it falls down or sinks in the water? 12 minus 2, 10 kgf. There is an apparent loss of 2 kgf. Interestingly, the upthrust in both the cases was same. Did you get the right answer? Well, if not, then watch the whole video again and understand the concept. Finally, let's talk about the Archimedes principle. I've already explained that indirectly, actually. Archimedes is famous because once he was, just the legend, the story goes like this. Once he was given an assignment by the king. The king got a crown, a gold crown, but he suspected if it was pure gold. So he asked Archimedes, his chief science advisor, if you can call him that, to find out. Today we have technology, we have machines, just touch it and we can know how pure the gold is or isn't. But we are talking about centuries ago. What would he do? So once he was in his bathtub and he was thinking about it, as all scientists do. We get our best ideas in the bathroom. Do you agree? So when he went inside the bathtub, he saw that the water level rose. And when he got out of the bathtub, he saw that the water level went back down. Because when you go inside the bathtub, you are displacing water. Then he had an idea. And he was so excited that he just ran across the street straight from the bathroom, if you know what I mean, shouting, "Eureka, Eureka, I found it." He went to the palace, and then he was able to ascertain if the gold was pure or not, because pure gold would have a fixed density, so a given mass of gold would displace a given volume of water. If it doesn't match with his calculations, then he would be able to say that it's not pure gold. So you can read more about it online or wait for my lecture if you have any questions. But let's get back to Archimedes' principle, which states, whenever a body is immersed in a liquid or a fluid, partially or completely, it experiences an upthrust which is equal to the weight of the liquid displaced by it. Now, I've already explained this actually. If you have a Eureka can, fill it with water up till the mouth, have a beaker out here, immerse an object in it. Let's say its initial weight was 15 kgf. And the liquid displaced by it, let's weigh it. We see that the liquid displaced by it has a weight of 12 kgf. Now, if I measure the weight of this object inside the water, obviously it will weigh less, right? What will be its weight? Tell me the answer. Well, it's going to be 3 kgf. The weight of the liquid displaced is equal to the upthrust, which is 12 kgf. So if the weight is 15 kgf and the upthrust is 12 kgf, what is the net force now inside water? 3 kgf acting downwards. The apparent weight is 3 kgf. The loss in weight, apparent loss in weight, is 12 kgf. The upthrust is 12 kgf. The weight of the liquid displaced is 12 kgf. So this proves Archimedes' principle, which is quite surprising, that the loss in the weight is equal to the weight of the liquid displaced. And if the weight of the liquid displaced is equal to or more than the weight of the object, then the object will definitely float, because then the net weight will become 0. Physics chapter 5 section A, Upthrust and Archimedes' principle, mark the definition of upthrust or buoyant force and the property called buoyancy. It's not Beyonce, it's buoyancy. Cancel experiment 1, experiment 2 and explanation. Write this formula on top. This is the master equation for this chapter. Upthrust is equal to apparent loss in weight is equal to weight of fluid displaced. Now mark this, give reason. A hydrogen or helium balloon will float and rise in air because even air exerts upthrust, and the weight of the balloon is far less than the upthrust. Now there are few conditions. In this case, the weight and upthrust are exactly equal. That happens when the density of the solid is equal to the density of the liquid. The net weight is 0, apparent weight is 0, because they cancel each other. It floats with its entire body completely submerged, so it is just under the surface of water. What if the upthrust is greater than the weight when it is completely submerged? Then it will bob up, and a part of it will be above the surface of water. So now it will displace only that much water as is required to float. That means the weight of the liquid displaced will be equal to its own weight. So if its own weight was 10 kgf, the upthrust even now is exactly 10 kgf. So in this case also, upthrust is equal to weight. So remember, whenever anything floats, whether it is completely submerged or partially submerged, the weight of the object is equal to the upthrust, and that's why the net weight is 0. The apparent weight or the net force is 0. So highlight this sentence in italics. Cancel this sentence. Characteristics of upthrust. It depends on a few factors. For example, volume of the body submerged, which is equal to the volume of the liquid displaced. That's capital V. It depends on the density of the fluid, so that's rho. Density of the fluid, not the density of the object. And it depends on acceleration due to gravity. So the formula for upthrust is V rho G. There is one more characteristic. Weight acts downwards on the center of gravity, but buoyant force acts upwards on the center of buoyancy. In this case, the two centers are the same. But here,
you can see that the center of buoyancy is a little below the center of gravity, because center of gravity is like the midpoint of the entire object, but the center of buoyancy is like the midpoint of only the submerged part of the object. Center of gravity will be explained in detail in 10th standard. Now cancel this paragraph and mark this one as a GR, which says that even if a bunch of feathers has the same mass as a pebble, since it occupies more volume in air and it displaces more air, its upthrust is far greater. And that's why the pebble will reach the earth faster than the feathers, even though acceleration due to gravity is same. The next example shows that mercury, being denser than water or glycerine, would exert greater upthrust. So a cork would submerge more in glycerine while floating and less in mercury while floating, so that in each case it will be able to attain weightlessness by displacing only that much liquid as is required for it to float. That means in both the cases, while floating, the upthrust acting on it will be equal to its own weight. Nothing more, nothing less. What is the reason for the upthrust? Well, we know from the previous chapter that as the depth increases, the pressure also increases. So the pressure, downward pressure on the upper surface is less than the upward pressure on the lower surface, because there is some depth difference here, thickness difference. The lateral pressures are all equal and opposite, so they cancel each other. But because of the difference between these two pressures, there is a net upward pressure, and that multiplied by the area is nothing but the upthrust force. But what if the depth difference was very less? What if it was just a sheet of metal, like a lamina, very, very thin sheet? Then there would be no upthrust acting and it would sink. Now there is a proof of the formula for upthrust, which is not in syllabus, but you can mark it as read in your school if they teach it. Then you may have to study it for your school exam, although it's not for syllabus. We do have numericals based on this formula. V rho G, volume of liquid displaced, which is equal to the volume of the object submerged, density of the liquid, not the solid, and G's value is almost constant everywhere, so we don't talk about it much. The factors are again volume and the density respectively. Experiment this is cancelled. Mark this as a GR. If you weigh something in air and you get the weight as, let's say, 5 gram, but if you weigh it in vacuum, it would come as 5.1 gram, and that is the actual weight. In air we have a slightly less weight because there is upthrust exerted in air as well. Now Archimedes' principle, which he discovered during his Eureka moment. Do you know the Eureka story? Now the principle states that when a body is immersed partially or completely in a liquid, it will experience an upthrust, and that upthrust is equal to the weight of the liquid displaced by it, and that is also equal to the loss in weight it will face. The experimental verifications are all cancelled. Now remember the 3 cases here. If the weight is greater than upthrust, it will sink, because even the density of the object was greater than the density of the liquid. If they are equal, then it will float, but it will be completely submerged. And if the weight is less than the upthrust, then also it will float, but it will not be completely submerged. It will be submerged partially, because it would submerge only that much as is required for it to float. And again here, just like here, the net force or net weight will be 0. And here, the density of the solid will be less than the density of the liquid. Experiment 1 is a give reason. Why does an iron nail float on mercury and sink in water? And why does a cork float in water? Well, we know that is because of the difference in densities, but now you can even talk about the upthrust. In case of nail, iron nail, the upthrust by water is not sufficient. It's less than its weight. But in case of the cork, the upthrust is equal to its own weight. Experiment 2 is cancelled. This is there, and cancel this part. Even in the exercise, there are some very interesting questions. Whose answers may also be given. They are application based, so make sure you study the exercise as thoroughly as you study the chapter, because there are some questions in the exercise which are not covered in the theory part. After all, this chapter is very application based. Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.